Welcome to this episode of My Ramblings. This episode, electromagnetic theory learned at the university and practical applications to facilities electrical engineering. Wow, you know, who'da thunk? Anyway, one of the projects I was asked to look at was to look at quality lighting, and I did a number of these evaluations throughout my career. This is like one of the first ones I ever did. Um, you ever notice, and I don't mean this as a negative comment, that a lot of Navy people, they retire and they buy a boat? Well, it's because they're the Navy and they're so used to having a boat or ship for most of their career, and they spend so much time cleaning and scraping and painting boats and stuff that they almost have to have one. So you could imagine the Navy does a lot of ship painting and stuff. Um, so I got called out to have a look at one of their painting facilities because they were having trouble with the lighting. They couldn't see very well for some reason. Okay, so I'm going to go out there and look at it. And I think the guy that was sort of involved in the project was our fire protection engineer. And I think what they had done was they had taken some temporary lighting systems and installed them all along the long wall, or at least part of the long wall. And, just to simulate, okay, well, yeah, we could see good now. Um, and, the thing you have to understand about fire protection engineers is they're kind of like architects. Um, this joke was actually told to me by an architect. So, what's the difference between architects and engineers? Well, the difference is that architects can't do math, and engineers couldn't draw a picture if it meant, even if it meant they could have made $1 million off of it. But. So anyway, um, and this particular fire protection engineer, almost any other table he would have showed me, he would have been correct. I don't think he thought too much of university knowledge. He thought, working for a contractor made people better engineers. I think working for a contractor made people better construction contractors, but I've never worked for one, so I couldn't tell you. But I think they have. It's like trying to compare engineers and electricians. Why would you do that? They don't perform the same functions. I really have no idea how an electrician does his job. I don't have those skills training. I never went through any kind of apprenticeship. Just like a construction contractor, he's running a business as well as coordinating all these trades. And nothing in my career experience, ever had me do something like that. So I'm not against construction contractors. They do what they do, and we do what we do. But so this guy was trying to tell me, well, see this, and almost any other table he would have pointed at, he would have been correct. But this particular table, he said, there's a skin effect. What the hell do we need calculations for and shit like that? And I take a quick glance at the table, and he's comparing two columns of DC values. All right, most tables only have one value of DC, one table of DC values, unless you've been through an electrical distribution course at the university if you're studying modern power systems. And you see sometimes there are tables that have two DC columns. And so you try to say that skin effect. Well, skin effect is due to a phenomenon that occurs where the frequency of a wavelength traveling through a wire may not penetrate the full depth of the um, of the diameter of the wire, and so in effect you don't get the effective full cross-sectional area for the traversal of current. And this stuff is optimized in manufacturing for 60 hertz when it's for a 60 hertz application, so it's usually not a problem, except when you get into the higher wire sizes, you start to notice you don't have the same relative increase in current capacity. I'm not going to go there, as you would as you seem to get for a while in the smaller sizes. It's because, if I remember correctly, I got to go back and look at the tables. This stuff is complicated. You know, it's not stuff you want to try. I ever try to do off the top of my head. You know, I need to make sure that I was on the right page. But really, so what he was looking at was he was looking at a table that showed solid conductors and twisted conductors, and you know, the way that was described to me is that, you know, because the conductors have additional length, you know, unless it's actually, you know, unless the diameters are adjusted to compensate for it, you actually have slightly more resistance, or you can have slightly more resistance in the twisted conductors. Yeah, you got to account for, well, the diameter smaller, so you kind of have more resistance, but you got a bunch of strands running together, so it's sort of a parallel combination. And then, you know, it just depends on, you know, which factor predominates, where you could say, well, rule of thumb, this is the reason why. So anyway, I go out to this paint facility. First thing I notice is, well, it's kind of dark. I mean, the walls are white. That's kind of good. You know, generally, that's a higher, you know, reflection of light, but it's concrete, which isn't such a great reflector. But all their lights are focused like in this linear center pattern configuration. And I think at the time I could distinguish between a high bay and a low bay fixture. And they were kind of long fixtures, which would mean high bay. So all the light was directly downwards. So you're going to have, sure, there's still going to be some beam spread and, you know, and refraction as it hits the edges, whatever that technical term would be. But for all intents and purposes, the primary component was a direct component directly down onto the object. And so not as much inner reflection as you would have had as if you had had a low bay fixture where the light is intended to be distributed out. But he was talking about putting fluorescence along, so I went out and I got back to the office. I'm looking around. I had a couple of catalogs. Looking in, you know, for fluorescent fixtures that you could mount along the wall. It still would have been a band-aid approach, but you know, that were rated for the hazardous classified location that, you know, spray paint is classified under. But I couldn't find any, and so in my write-up, I just pointed out that, look, you really got to start over. You got to take out that narrow concentration of light and get some light that will spread and inter-reflect. And, you know, as a GS7, 9, whatever the hell I was at the time, I mean, even if I just got off the PDC internship, I still would have been relatively, in terms of experience, a junior engineer. And by that time, I didn't even know how to go about hiring an A&E to come in and design it. You know, it was just, so I wrote it up and I explained that, well, all your light is focused down and stuff, and really you have to take those out, get a spread layout, and, you know, do a lighting system that will cause more reflected light to come in. I suppose as a follow-up, then, you know, somebody could also, if when they designed it, you know, provide more focused lighting and stuff, you know, in areas where they determined it would be deficient. But really, that was electromagnetic theory being applied, because light is part of the electromagnetic spectrum. The Illuminating Engineering Society recognizes this. I think they mention electromagnetic spectrum, but they shift in on terminology. But essentially, they're recognizing it, that their terminology is still based on. And, you know, electromagnetic spectrum consists of every frequency, if not including zero, all the way up to, if not including, infinite frequency. You know, every grouping of wavelengths has their own special characteristics. Sound basically is an electromagnetic wave. It will travel through some surfaces, some substances. Light, however, won't, in most instances, go through an object. You know, if it's glass, it'll transmit. So, but you can generally assume that light travels in a straight line. When it strikes an object, it will reflect off it's, you know, the angle it reflects off as is equal to the angle of incidence and stuff. So that was sort of the starting point. Um, anyway, so if you're a junior engineer and stuff, no matter, you know, sometimes what you learn in college is still directly applicable to working in facilities engineering. Anyway, hope you enjoyed the insight if you didn't already have it, and have a nice day.